Thank you for coming to this talk on automation and developer infrastructure, how we empower engineers to move from idea to production. I'm Alex Thurlow. I'm an engineering manager here at Indeed, and I help people get jobs. And I do that by building tools that help our development and release process, allowing our developers to concentrate on writing new features and to get those features to production quickly. Who are we? Who is Indeed? We're a job search engine. Over 180 million people come to Indeed each month looking for jobs. Job seekers can specify what they're looking for and where they're looking for it. And we return the most relevant and up-to-date job listings. Job seekers can also post their resume for easy application to jobs online and to allow employers to find them. We make tools for employers to post their jobs and to search for job seekers' resumes. And we have a program called Indeed Prime that matches top talent with top employers. With all these things we're trying to accomplish, we have tons of other applications, both for internal use and client use. But how do we know what the next thing to build is? Well, the mantra we say around here all the time is, what's best for the job seeker? That should drive our product development choices. But how do we know what's best for the job seeker? Well, we use data-driven product design. In a previous talk, we dug into how we used measurements and A/B testing to choose the right products to build. I'll go into a brief overview, but if you'd like to see the details, I urge you to go watch this other talk. Many of you have seen the concept of build, measure, learn from the lean startup cycle. It says that you should build a minimum viable product, put it in front of your users, and then measure how your users interact with that product. Then you can learn from your measurements to drive what the next thing to build is. And you keep doing this iteratively until you've built the right product. Many startups have been founded on this methodology, and Indeed is no exception. We still do this today. However, we do like to use the word deliver rather than build, which really stresses that you have to get your feature in front of job seekers before you can measure it and before you can learn from it. This would be in contrast to some software methodologies that might do frequent internal builds, but release to production less often. Data-driven product design requires quick feedback. If you don't get your features in front of users, you can't measure it, you can't learn it. We believe that you have to do this rapidly. The concepts of doing this rapidly are a subject we call engineering velocity. Again, we've talked about this previously, and I'll give a brief overview, but if you're interested in more details, we have another talk to watch. Engineering velocity encompasses many subjects, including developer productivity, software architecture, and the release process. I'm not going to talk about our software architecture today because we talked about that a lot in our previous talk. However, it's important to understand that we do have a service-oriented architecture here. One of the reasons we have that is it means we have many small independent applications. And having those small independent applications means small teams can make small changes and release them to production quickly and independently. And that helps them deliver on the deliver, measure, learn cycle very rapidly. Tonight, we're going to concentrate on the deliver step of the cycle. And delivery starts with developer productivity. John Hanks is going to talk about one of the ways that we address that.
Hello, I'm John Hanks. I'm a software engineer here at Indeed. And I help people get jobs by making developers more productive and better able to get features into production quickly. I'm here today to talk to you about Hobo. Hobo is our system for automated developer provisioning. When a new developer starts at Indeed, we have one goal for them, and that is for them to get code into production within the first week. The reason we do this is we like to introduce them to our deliver, measure, learn cycle immediately and show them all the steps that need to be taken along the way to get code into production. We also want to show them that they can contribute immediately. In the early days in Indeed, when a new developer would start, we would pair them up with the experienced developer as a mentor. The mentor would help them get their system set up, get the application set up that they're working on. This ended up usually being the experienced developer would copy over their computer and application configuration for the new developer, and it would generally end up taking 2 to 3 days to get the new developer set up and running with the application that they'd be working on. The problem here is it only left a couple days for the new developer to learn how the product works, build their feature, deploy it to QA, and verify that it works in QA, and then deploy it to production. Another thing we like to do with new developers here is we put them into a team rotation. The reason we do this is it helps new developers understand how we work at Indeed, helps them get a better understanding of what the different teams do, and it also helps us find the best fit for the new developer, team-wise. The way this works is the new developer will spend 4 weeks on 3 different teams. And the problem arose that it had the same challenge. They'd be facing the same setup challenges and with their mentors on all of the 3 teams. So it ended up being several weeks of unproductive and uninteresting work for both them and the mentors, which caused a lot of frustration. Our experienced developers would have a similar problem because we like to encourage our experienced developers to switch teams every once in a while to find a product that they're really interested in working on, and also to, if they find a need in a product that another team works on, to contribute directly to that team. So they would have the same problem. And as Alex mentioned, we use a service-oriented architecture here at Indeed. So for example, if you're just trying to run a single application, here Search Web App, and you need that to communicate with a single database, it's pretty easy to run both of those on your local development machine without much problem. But at Indeed, our application stacks tend to look a lot more like this. You'll have the Search Web App application you might be developing for, and it will need to communicate to several different services who each might need to communicate to a database or a data file object. In reality, our application stacks are much more complex with many interdependent services and applications that talk to different databases and so forth, but we'll stick with the simpler example for this presentation. So the need arose that developers would have to run many different interconnected applications just to develop a feature that they're working on. And this is what caused the problems with the long setup time and why it would take so long to set up an application for a developer to work with. We're growing quite quickly at Indeed. As you can see here from this chart, our active developers. A while back, we would have only a few new developers starting each month, but more recently, we've had as many as 50 developers start in a single day. And with that kind of growth, the mentorship program we were running just didn't scale. The experienced mentors would have to be paired with multiple new developers, and they'd spend all their time helping new developers get set up and not have any time to develop new features or support the products that they work on. So we decided that we needed to use technology to speed up developer provisioning. And when we started this project, we looked at what was available in the market, and we said Vagrant seemed to be a good solution for us. So we built a solution using Vagrant. Now what Vagrant does is it automates the creation of a virtual machine. So it can automate the creation of a virtualized development environment, which would be reproducible each time you start it up. So for example, if we wanted to use it to start our Search Web App application stack, in the Vagrant configuration, we would tell it how to set up the operating system, how to set up and configure that, how to set up and configure any other software needed like MySQL or Mongo databases, then how to set up and configure each of the different services, and finally how to start the Search Web App. All that would have to be stored in the Vagrant file, and you have to get it all correct. So this kind of worked. The developers would set up the Vagrant files and implement this for some projects, and there was a bit of success. We had some good results. From this solution, we got reproducible environments. The environment would be the same if you were to destroy it and recreate it, which, as anyone who's worked with virtual machines in development knows, that sometimes you just need to restart your environment. You need a fresh environment, so you have to destroy it and recreate it. We also got configurations that were shareable between developers. This configuration file could be shared by just checking it into source control, and other developers could easily get to it and use it. It also lowered our general setup time for the projects that implemented this to less than a day, which was a pretty good improvement. But along with the good from this, we also found that our solution didn't quite meet all our needs, and there were some bad parts. So the environments were still pretty slow to create. It could take 15 minutes or more to start up your Vagrant environment. The reason for this is when you start a Vagrant environment, the first time especially, you have to download the Linux distribution that you want to run. Then you have to download and install all of the required software that you're going to need. And some of this software might have to be built from source and installed. That could take quite a long time. All that has to be done before the application stack can start. So then you start each of the services in the correct order, and then you start up the application that you'd be working on. This all could take quite a while. It could take up to 15 minutes or more. We also found that the initial setup, especially for large and complex application stacks, it was very difficult to set up these configurations correctly. So, for example, if I was setting up the Search Web App configuration to run the Search Web App stack, I would have to correctly configure how to start up each of these services and then the web app. And I'd have to put all of that information and configuration in the Vagrant file correctly in the right order and test it. Now, this could work, but the problem arose when you also say you wanted to run the Employer Web App. Employer Web App happens to use a lot of the same services as you see here. So now you have to also put the same configuration to start up each of those services in the configuration file that defines how to start the Employer Web App. So if any of these configurations startup sequences changed, you'd have to update that configuration in all the different places who happen to use them. And so we ended up with duplicated code across several different projects, and it was prone to errors. Another issue is that if you happen to want to run both of these at the same time, you'd have to run multiple virtual machines, which would take up a lot of system resources. And you'd end up running the same services multiple times because they'd be running on both virtual machines because they couldn't communicate. This leads to the next problem, which is that using virtual machines has quite a bit of memory overhead. So if you're just running your standard system, the operating system controls all the memory, and it will allocate the RAM as needed to any processes you're running. However, if you want to run a virtual machine, you have to manually partition how much memory the virtual machine is going to be allocated, and then the virtual machine takes over managing all of that memory. So now you can easily get into a situation where you didn't set up the configuration quite right, and you're squeezed for memory on one side of the partition while the other side of the partition has excess memory. Another problem with our solution was that due to the difficulty in setting up these configurations, we had limited support for different application types. At Indeed, our developers develop application types of many different kinds. They develop Tomcat web apps, Java daemons, Python cron jobs, and many others. And it was difficult to set up these configurations, so we weren't able to build and test a lot of them. And another issue that arose is that we only built and tested the system on Linux. At the time, this seemed to be the right choice because we only use Linux desktops for development, generally. However, then we found out that we're all getting MacBooks as our laptop. So this arose a problem. And now with the new laptops, we'd be back to the old problem of spending 2 to 3 days to set up the development environments. So given those problems with our solution, we said that we need to go back to the drawing board a bit, and we look back at our deliver, measure, learn cycle, and we learned that we needed to build a new solution that would solve some of these problems. And the solution we built for this was called Hobo. And the reason it's named Hobo is because that's a synonym for vagrant. So we had several goals when we were designing the Hobo system. The first goal was that it should support all different types of applications our developers were building and wanted to build here at Indeed. It should also be quick to start up the applications. You never want to put extra time into the lives of developers as they're working. It's never a good idea. It needed to support OS X to support all those new MacBooks we'd be getting. And it needed to support our complex application stacks simply. It also needed to be simple and easy for developers to use. They have a lot of complex stuff they need to know, and this didn't need to be another one. And it should be easy to share configurations and the system between developers. So given those goals, we looked at what was now available in the market, and Docker had been released. And we found that Docker was a really good technology choice for this project. So we decided we'd build our solutions based on Docker. So let me give a little bit of a introduction to what is Docker. When you run traditional virtual machines, each one has to have its own system kernel, system resources, system files, and memory. And for each one you run, you have to duplicate that. However, with Docker, the Docker system allows you to run containers that use a shared system kernel, shared system memory, and containers run based on images that use a layered file system to allow for shared common files. So let me explain a few Docker terminology so we could talk about what we did. In Docker, an image is a template for an operating system file system that describes which files are on the system, which applications are installed, and how they're configured. In Docker, a container is a running instance of an application. And you can also run multiple containers from the same image. So for example, if I created an image with MySQL in it, I needed a MySQL database. If I then needed to run two MySQL databases, I can simply start up two containers based on that same image, and I'll have two MySQLs running. A Docker registry is a special server for hosting and sharing Docker image files. And it uses a syntax similar to Git for pushing and pulling the images. So looking back at our goals, already from choosing Docker, we already get a couple of these goals solved. Docker's containers are very quick to start up. Generally, they start in under 100 milliseconds. And Docker already supports OS X out of the box. It does this by using a virtual machine itself, but it manages that and makes most of it transparent to the user. Now, to solve the rest of our goals, we knew we'd have to build some of our own solutions. So how do we support all different types of applications? The way we decided to do this is that we would create a Docker image for each type of application and each type of resource our developers wanted to use. And then we publish the image to the Docker registry where they can easily fetch it. As an example of this, say you wanted to run a Java daemon. Now you need CentOS with Java installed. So what we do is we would start an image based on CentOS, we'd install Java into it, and build the image by installing Java into it, and then we would publish that image to the Docker registry as Hobo Java. Now, the great thing about Docker images is they allow for an idea of inheriting or layering. And the way this works is much like inheriting in software development. If I have an image and I then inherit an image, then the new image gets all the stuff the previous image has, and I could build on top of it. So imagine we needed to run a Tomcat application, and for Tomcat we needed Java installed as well as Tomcat in CentOS. You might think we need to install Java and then install Tomcat. However, we already have an image with Hobo Java, called Hobo Java with Java installed in CentOS. So we can start from that image, build a new image that is just us installing Tomcat into that image, and we can name that new image Hobo Tomcat. And now any Tomcat web app can just use that image to start and run. So what we did is, for all the different types of applications and resources our developers like to use, we created an image. And we created images and configured them as close to production as we could so that when developers were developing, they'd catch bugs earlier. And these are some of the some logos of the different types of images we created and can use in the Hobo system. Another great thing about this is that if we need to make an update because the configuration changed or we found a bug, all we have to do is update the image ourselves, build the new image, push it to the Docker registry, and then all developers who use that image will automatically get updates. Another useful thing is that Docker Docker, the company, hosts their own registry, a public registry called Docker Hub. And there you can find 150,000 plus images of all different sorts that you can use to learn or build on top of. So now that we can support all different types of applications, how do we support complex application stacks? If we recall, when we wanted to run a search web app, we also needed to run 3 different services, as well as a resume database. Here happens to be a database that needs to be run. The other job search index and GeoIP database are file objects. So now if we want to run this stack, not inside of a virtual machine, rather using Docker, Docker is designed to have one process per container. So those 5 different things now become 5 containers instead of one virtual machine. We have the search web app in a single container, resume service, resume database in a single container, and so forth. And now if we also want to run employer web app, we just have to start another container running employer web app, and it can reuse and communicate with the other services that we're already running. And if a developer makes changes and they want to test those changes and see how they're operating, all they have to do is restart the container running the application that they're making changes to. Now, if everything's running in a single machine, like a virtual machine previously, it's really easy to network all these services together. I can use localhost to communicate with any of them. However, with Docker, now we have the idea of mini machines. And so each of these machines has a different IP address that Docker assigns locally, and we need to know the IP address to communicate with them. So we need the idea of service discovery. Service discovery is the idea of given that you know the name of a service, you can look it up and find out where it's running and then be able to communicate with it. And for service discovery, we chose to use an application called Consul. And what we do is we run Consul in an additional Docker container that Hobo manages and keeps up on the developer's machine. And what Consul is Consul is a key value store that is geared towards service discovery. And the great thing about it is it provides both an HTTP and DNS interface. Now, the way we use Consul is that when we start up a new container, we take the name of that container, here user service, we take the IP address that Docker has assigned to that container, and then we use the Consul API to register that container with Consul. And now we can simply do a DNS resolution on the node.consul domain, and we will find, we can use the name user service and find out exactly the IP address of where it's located. And now the great thing is that all of our configuration files and settings can use the name of a service, the container name, to reference that service, and so they don't have to know the IP address when they're setting up configurations. So now that these can communicate, how do we make sure that we've started up all of the many different dependent applications in the application stack? And for that, I want to give you an example of what our Hobo config file looks like. Hobo config is a file that sort of explains to Hobo how this application works. If you look here, you can see each of these in brackets is the name of a container. And the type there just tells Hobo what type of container it is. So the MySQL and Mongo containers are resources, and Hobo is smart enough to know that resources generally need to be started and up and running before an application starts up and runs. Another important setting here is the dependencies, and you can tell Hobo which other projects you depend on, and as long as those projects are set up with Hobo. Hobo will then look through your file system, find the projects, parse their Hobo config file, and then build a dependency graph and start each of those up in the correct order to have your entire application stack up and running easily. And then for another example, here's the user service Hobo config file. Very simply, it's 2 containers, and it doesn't have any additional dependencies. So with all those implementations, we can now support complex application stacks simply. And it becomes easy to share. All these configurations can be stored in the source code repository with the project. Now, how is this done? So this is sort of an example of a basic project. You have your source code, some various other files, and this is sort of the root of the project. So all that has to be done to set up Hobo is a Hobo directory is added to the root of the project. Within that Hobo directory, you create directories that each define a container that Hobo will start and manage. Here, as in our previous example, we have the job service MySQL, and job service Mongo containers. And this is also where you store the Hobo config file. So let's have a look in one of these container directories. Inside of here, there is the config directory. That just holds configuration files that the application will need to run and operate. We have a Docker file, and we have a run.sh file. Let's have a look at the Docker file. The Docker file is just a standard Docker file, and it explains how the image that this application, how the image is built that the container running this application will be built. So here, this application doesn't need anything in addition to Hobo Tomcat, so it just derives from that. If the developer also wanted to install additional applications or software, they can do that using standard Docker file syntax. Let's look in the config directory. In here, you'll just find basic configuration for an application. And this is supposed to be general configuration that can be checked into the repository with the application that a new developer starting the project for the first time would expect to have so that the application runs correctly. You can also have a directory called myconfig. If you have this allows you to override those configuration files. To do that, you would simply take the file you wanted to override, copy it into myconfig directory, and then you can make any changes you want in that file. And then Hobo will smartly load in that file instead of the original when it starts the application. There's also the run.sh script. And this, what's in the run.sh script? It just simply tells Hobo how to run the application. So in there we have the start and stop commands for how the application starts and stops. Developers can set environment variables such as the Java ops or other environment variables that they want to have. And also volume mounts are defined here. What are volume mounts? Volume mounts are how you load data into the container at runtime. And they're much like mounting a hard drive. It's simply how you mount files that are on your host file system and make them available to the running application in the container. So what kind of things do we mount into the containers while running? Well, the developer is developing and changing code, so we need to mount in the built code to run the changed application. We mount in those configuration files, and this is the time where Hobo smartly figures out which ones are overridden and mounts in those in the correct way. We mount log directories, so logs for your application will be stored on your local file system, and the developer is able to read and view those logs even if the container is destroyed or restarted or not running. And we also mount data directories. So data directories would contain any sort of data file that you need to make available to your application, such as artifacts or index files. It also might be, if it's a MySQL container, the files on the system that define what is actually stored in the MySQL container. That way, if you restart the container or destroy it and recreate it, you still have the data in your database. So with all this, it was important that we made this simple and easy for developers to use. So let's look at what is the experience like now for a new developer starting at Indeed on a project that's had Hobo set up. Well, all they have to do is clone the repository we get, run ant hobo deploy, and Hobo takes over and does everything else. And within 5 minutes, hopefully, everything is up and running. Their complex application stack is ready to go, and they can start development. So we'd like to share some results of how this has gone and how this has resulted at Indeed. So here's a graph of our active usage. We don't mandate or dictate that anyone has to use Hobo, so this really represents the adoption rate of teams and engineers here at Indeed. And as you can see, it's grown quite well. We've had over 330 projects that have been configured for running in Hobo. Here's a quote from a developer Sometimes I need to run apps from other teams, and the first thing I look for is this hoboed? If so, I'm happy. And so we also improved a key process. So the process of when you're developing and you need to completely wipe out your environment and start afresh. We took that process down from 15 minutes to about 30 seconds. The result of this is if a developer has to do this only 10 times per week, then we've gained 120 hours per year per developer. The developer is able to remain focused and remain in flow and continue working on their project. So we'd also like to share some lessons we learned and some takeaways from this. We found that for our use case, volume mounts are very useful. There's a lot of ways to load data into Docker containers, and Docker makes it easy to do in a lot of different ways. But for the use case of having a developer and wanting to load in data on their machine and wanting to make it available, no matter if the containers are destroyed and recreated, volume mounts were quite useful for us. We found that it was very important that we made it easy to use in the default case, but also fully customizable. So for kind of a default project without a lot of special configuration or special software needed, it was very easy for a developer to set up Hobo. We had a script that did most of the work. It would create the Hobo directory, create all the configuration files that are needed, and include comments in them telling exactly which things can be changed and which things can be customized. So this made it really easy for developers to set up Hobo for the first time, made them more comfortable, and then they were much more willing to move it on to other projects and use it in more complex use cases. And then making it fully customizable was really important. This is because it allows developers to do anything they need to when they're starting up, when they're building, or when they're running their application. And it also meant that developers came up with ways to use the Hobo system that we didn't even think of when we were building it, and were quite useful. And another takeaway is we found Docker to be a great technology, but Docker is in heavy development and they're moving very quickly. They're constantly releasing new versions with many new features. And since we started, they've also implemented features that would make a lot of the things we had to build much easier. So if you're looking at using Docker, make sure you read up on all their features available and keep an eye on their moving development. With that, I'd like to give it back to Alex to talk about our release process.
Now that development's taken care of and perfect, I'd like to talk to you about automating release management. This is what it looks like to get a feature released to production in Indeed. If you're trying to read this, you should stop now. It's obviously far too complicated. It has a lot of steps, and it used to have a lot of manual steps. So I'm going to talk about why this is so complicated and what we did to fix this. So first, why is this so complicated? Well, and yes, like I said, complicated and manual. We had a few goals we wanted to fulfill for our release process, and that's why we had all those steps. So, main goal, understand which features were being released. This might seem obvious, but in a collaborative environment like ours, it was really easy to end up with code in applications that you wouldn't know was there, that came from some other team or some other developer, so you'd need to understand what you're releasing. And also, in our interconnected system, there's a lot of interdependencies between products. So we have a lot of cross-product dependencies and even dependencies on other teams. And it was very important to understand those so we get features out in the right order to keep things working. A bug that gets out to production could cause millions of job seekers to not be able to find the right jobs. So we wanted to catch those bugs before they got to production and do it in such a way that kept us moving quickly and kept the development process flowing. And our data-driven development culture doesn't stop at the product level. We wanted to have data about the release process itself, so we could go analyze and improve it after the fact. So we wanted to record all the details about each software release as it happened. With these goals in mind, we've come up with this complicated system to do our releases. And it has many different parts of it, but let me go through the life of a feature and explain a few of these pieces. At the high level, you can look at it in about 4 steps. You develop the feature, you create a release with this feature in it, you test that release, and then you deploy it to production and record what it is you released. To help do that, even at the beginning, we use some standard development and project management tools, so I'll go over them. For tracking our issues, our bugs, and new features, we used Atlassian's Jira. We found it to be flexible and customizable, so it can track everything we need to track about every feature and every release. Code reviews are extremely important in our environment, and we chose to use Atlassian's Crucible to help accomplish that. The Jenkins automation server does our builds and triggers deploys. And for source control, we use Git. Specifically, we use the open source GitLab server to host our repositories. So, quick digression about Git. Git is extremely powerful. It's become an industry standard partially because of that power. However, that power comes at a cost of complexity. I'm sure many of you, when you were learning Git or training somebody how to use Git, you ended up with a repository in some weird state. You didn't know how you got there. You had code you weren't sure about, and you just didn't know what was going on. So we found it was important to choose a standard way of using Git. And there's a few of these published around different strategies for how to use it. We chose one called Git Flow. It's fairly commonly used, fairly simple and well understood, but still powerful enough for our needs. Basically goes like this. There's a shared branch. In our case, we call it master. Developers do all their feature work on branches. We name them after the Jira issue itself, so we know which branch goes with which feature. When the developer's finished, they merge that branch back to that shared branch, so all code is mixed together, and then we can cut a release from there. Development process probably looks a lot like what you would expect. Developer works, they work on their feature branch. When they think they're done, they push that branch, they resolve their Jira issue to say that they're done, they open a code review. Because, like I said, code review is really important, the developer should take all the feedback from that review and keep fixing their code until the code review gets sign-off and then somebody else says it's ready. As soon as it's ready, the developer creates a request to have it merged into that mainline branch. Note that feature code can also be in libraries. We have a lot of different applications. A lot of them need to do the same things. We want to share code rather than duplicating it and copying it everywhere. So a web application may have a library that knows how to do common web app actions. It probably has a library that knows how to talk to databases, and it may have a library that knows how to talk to one of our specific API services. And note that our applications could actually have dozens or hundreds of other libraries. So a developer feature may come in multiple different repositories. But the development process stays the same even with those different repositories. We go through the same steps. But once they're done with those steps, the developer passes the responsibility to the release manager. Some companies have separate teams that do their software releases. We believe that our engineering teams know best when to release their own software, what to release, and how to release it. So we give them that power. Most teams rotate the release management duties. Each one holds it for about a week and rotates through. And the release manager is responsible for executing on these goals of the release that we set out and making sure that they get done. They're basically responsible for this huge chunk of the graph, which is a whole bunch of manual steps and kind of a pain. Let's start with what they did at the beginning. You want to define a release. What is a release? Well, in practical terms, the release manager would make a branch off the master branch to define where to start doing the release in code. Then they would lock down all the libraries to specific versions. We assume that all the versions, the newest versions of our libraries are the best, and we don't want strange upgrades coming in the release process. We want to hold a version throughout the release so we can test it properly. So we want to lock those in. After they have a release, Jenkins does a build, runs some tests against it, and deploys it to a QA environment. Now gets into the part of understanding which features are being released. With this code and some libraries, how did they actually know? Well, fairly complex and manual process. They really had a mystery on their hands because of all the different systems that the data could come from Jira, Git, Crucible, etc. So they would start. We had a dashboard in Jira, that would show everything that was supposed to be in the release, whether a developer had marked it as ready or somebody had requested it be targeted to a certain date. So they would look at that, and then look at a Git log in the application. Make sure that each commit in the Git log corresponds to a Jira issue. Each Jira issue has some commits. And they had to do that not just for the main repository, but also for each library version. And because, like I said, there could be hundreds of libraries, usually release managers wouldn't actually look at every library. They would just look at the things they were expecting to have changes or expecting to have things they needed to care about. So a lot of things weren't getting looked at. And then they know what code they have. They need to make sure that it's code reviewed. So again, going back to Crucible, making sure that each thing is reviewed. Beyond that, we needed to understand what order things need to go out in. Again, we use Jira for tracking some concepts with this. Jira has a built-in concept of a fixed version. Each bug or feature gets associated with that version, so we know that they're going out in a specific release. We made our own concept of a deploy ticket, which was a central place to track what state the release was in. So it could tell what environment the release was in, people could make comments and talk about the status of that release. And it was a central location for any interested party to just track what was going on. Because a feature can depend on another feature, for instance, if my web application needs data from an API and that data is not available until some feature is deployed, I need to make sure I deploy those in the right order. So we use Jira issue relationships to say that our feature depends upon that other feature. And transitively, the deploy itself depends on that other feature. So the release manager would go and update the deploy ticket and say that that deploy depends on the feature. Once you have a release, it's time to do the testing cycle. And we wanted to address our bugs quickly. We have a really good QA team. Our QA analysts are excellent at finding bugs, which unfortunately means it's pretty common to find a bug once it's in the QA environment. And that is probably what you'd expect. QA analyst finds a bug, they reopen the issue for the developer fixes it, pushes it back into the release, another build, go back to QA, and that cycle needs to continue until a QA analyst signs off and says that the release is ready to go to production. Then we deploy to production. And I'm going to completely gloss over this because this is a deep enough subject for another talk, and we'll save it for that. But assume that we've had a smooth production deploy. Now that it's deployed, we need to understand what we deployed. We need to mark it. We also have some cleanup to do in all these different systems. So many different things to do, usually mostly in Git and Jira again. This is what a Git repo might look like after a release. Simplified, of course. We have our release branch, we still have our master branch, and we have the feature branches from the features that were released. First thing to do, release manager needs to delete the release branch and make a Git tag in that location. The Git tag makes a permanent record in the repository that we can always go back to and say, this was released on this day, we know what went out. Then, delete the feature branches for the features that were being released. Now that they're out there in production, it's pretty unlikely we're going to need that branch again, so we can clean it out of the repo and keep things looking good. The master branch needs to have everything that was in the last release. When we start another release, we don't want to be missing anything, and there may have been changes on that release. So the release manager merges the deploy back to master, gets everything up to date, and now we're ready for the next release cycle. Then close the Jira issues that were released, close the deploy ticket, and mark the fixed version as released in Jira. So we're finally done with a release. It's all done, and a person had to do each one of these steps manually. But we did fulfill the goals of our release process. We understood what was going on, and things were kind of working. But we did know we had some problems. First, release management took a lot of time. All those individual steps just mean wall clock time for a developer doing each thing rather than writing code. It was also hard to understand what was in a release, thanks to different data being in different systems and it all having to be put together in different ways. All those different manual steps meant there was a distinct possibility for error. With that many, you could easily miss one or two, which could cause you a problem down the road. And the culmination of that meant that only our most senior engineers could handle releases. Only they had enough context in the whole system, knew enough going on to know all the steps to run through a release themselves. To put a number on this, A release with 4 features done manually took over 100 individual Git commands and clicks in all these different interfaces to get it out the door. And adding on an additional feature would add about 13 extra actions. Like John showed you, we're adding a lot of developers. New developers means we have room to work on new projects. We're always coming up with new ideas in the job search and HR space. Now that we have these developers, we want them to build new things. However, these new projects mean that we have more deploys to do. And these are new developers, not our seasoned developers, so they're not quite up to release management yet. It means that our senior developers are spending all of their time doing releases and have no time to work on these new features and do other interesting code. So we decided we needed to automate this process. You might ask why we would automate rather than simplify. Surely this process can be simplified. Well, it comes down to 3 main reasons why we couldn't. Number 1 is data. Our data-driven development culture says we need to collect all the data on this because you can't improve what you can't measure. We wanted to be able to analyze this process and improve it, so we needed to collect all that data. It was also important to keep a history. It's very important to understand when a feature is released and what was released so we can see how features interact with each other and how job seekers interact with each feature over time. And a transparent process was important. Because these applications depend upon each other, it's very important for other stakeholders like product managers or developers on other teams to easily be able to see what was going on in a given release or see when a feature was going out. So with that, we're back to needing to automate. We looked at what we needed to do, and a lot of it came down to having a lot of different systems in the release process, a lot of data in those systems that needed to be joined together, and a lot of individual actions that just needed to be done in the right order. We realized that if we could collect all that data in a single application, it would help a lot. So we built an application that integrated with all these different systems, Jira, Crucible, Git, and Jenkins, could collect all the data, collate it, and then also automate all these actions that had to happen in order through the various APIs. And we called this Control Tower because it gives us a view of everything and helps direct the release process. So how did it help us address the goals of the release? Well, how about understanding which features were released? Control Tower gives us a unified view of every feature that could be released and lets us choose and lets us see all the information in one place. This is obviously too much information, so I'll zoom in a little bit. Our top-level organizer is the Jira issue. So we put right at the front Jira key, the title, and the priority. Code reviews come right after that. Control Tower talks to the Crucible API, gets all the code reviews for the issue, and gives the status right there for the release manager to see. And we can differentiate between a code review being reviewed by a project owner, as in somebody who works on it all the time, between if any other engineer has reviewed it, actually if it's been marked defective, or if it has no code review at all. And we can also associate the Git information with each feature. We include the Git branch name, and Control Tower can actually do some introspection into the Git branch. It's pretty common for one branch to actually end up including code for a different branch. Those features are kind of blended together. Control Tower will look and warn the release manager that 2 features actually need to go out together. In this case, you can see that one of our features is marked as a required feature of one of the others. And so that helps the release manager do things correctly. And if they want to know more information, a single click shows all the individual commits that are in that branch so they can see the messages and authors and see what's going on. And even further, if they want to see the code in there, any branch link or any commit link will go to a page that shows a full diff of the code going out. So it's very easy for a release manager to see what actual code is in a release. And understanding their cross-product and cross-team dependencies becomes just as easy. We can again query the Jira API and ask about any issue dependencies. We see here that 2 of our issues depend upon other issues. So we're going to need to wait for those to get deployed and closed out, or we can choose to push these features back and release something else instead. It gives the release manager the power to see this information and make a good decision based on it. What about seeing feature code in libraries? As I said, this is something that was really, really hard to see before. With hundreds of different libraries, the release manager would have to look at what version they were pulling in, find the version from the last release, because it's not necessarily just the previous release, and do Git logs between them and do a bunch of operations. And with all that, basically, it wasn't happening. Release managers were not able to see what was in library code. Now, we integrated Control Tower with our dependency management system as well. It can look up and see what libraries you're pulling in. It knows what libraries you released last, and it can show every commit that came between. The main view shows commits that have been targeted specifically to this release, and there's another view that can also show all the commits coming in from every library, even transitively. And so this is brand new information for the release manager to help them see issues right up front. Now that we understand what we need to release, and we understand what order it can be released in, it's time to actually move on to creating the release. So remember, there was a bunch of manual steps in Git and Jira, creating a branch. We need to update Jira. We need to do issue dependencies. Now, that's a little form. Release manager chooses a date. They choose whether they want to upgrade their dependencies, and they click the Create button. That handles all those steps automatically and updates everything for them, including updating all those issue dependencies and everything. Moving on to addressing bugs, we really needed to address how we could track a release in progress to see how bugs were being addressed. The QA analyst would find a bug, they would reopen the issue, and that tells the developer that there's something they need to fix. However, the release manager also needs to know there's something reopened. We use standard coloring in Control Tower, green, blue, yellow, red for the different levels, and we can just highlight really easily, feature in red, this issue has been reopened, a clear message saying, hey, don't release this, there's some problem. Wait for this to get closed back out. Of course, that fix needs a new commit. It's on the branch. So developer pushes that, it's out there, and they'll resolve their issue to say that they're done making their fix. However, now we're in a really bad state. Jira says that the issue is resolved, but if we look at the Git repository, it looks like that feature is actually not in the repository. However, we know that we have 2 out of 3 commits that are there, and we specifically know that they're buggy commits and that we don't have the fix for them. Well, Control Tower finds this as well. Through introspection in Git, it can see that that feature was previously merged into the release and has commits there, but also has commits that aren't in the release. So highlight it in red, let the release manager know there are some commits here, you need to update your release, and additionally, it gives them a single button they can hit to update them. They hit that button, it merges that feature back in, and triggers another QA deploy, which keeps the process moving quicker and quicker. After the deploy, there's recording the release details and doing all of our cleanup. All these different things in Git and Jira turns into this. Single button, developer, when they're ready, they hit close release. And we still use our standard coloring, so the release manager can look and see, and if the board's all green, they're all done with their release. So we've taken this process and all these manual steps, and where are we now? These are the steps left to do by a human with just a couple of clicks to go between stages. Once that's all eliminated, the life of a feature starts to look a lot more like just develop, define a release, test that release, and deploy, without having to worry about all the pieces underneath. And that makes life a lot simpler for the developer. So how'd we do? Well, looking at release management taking a lot of time and all those manual steps, and our release taking 100 different things to do, that's down to 15 clicks and all in one interface, which makes things a lot easier. And that's not to mention just having the information available as a result of those. And our 13 extra actions per feature, it's down to 0. It's very little extra effort for the release manager to add another feature into that release. You can see here our deploys per month has increased dramatically. You may say that's just from having new developers and new products. We're also doing about twice as many deploys per project as we were before. So we've really been able to accelerate the pace, get features out quickly, and really execute on our development cycle. How about understanding what was in a release? Our unified interface gives all the information the release manager needs on one page. It's very easy to see everything, and with our color coding and pointing out errors, they don't even have to worry about reading everything. They just need to look and see the things that have been pointed out. And culmination of that, senior engineers knowing enough, well, we've given release managers so much more knowledge and so much more automation of their tools, it's reliable and it's less risky. Now, 57% of our developers are release managers, and that number is increasing every day. We even have some of our QA analysts handling releases rather than the engineers having to do it. Some developers are starting doing releases within 3 months of starting. In contrast, it used to take over a year. So what did we learn? Everything can be automated, really everything. We looked at this process. We had come up with a good process, but every single system that you work with in this environment has an API, has a way to automate it. If you're going to do something over and over again, it's worth automating it, and you can do it. Now, when we look at new processes, the first question we ask before we even get into doing it is, will we be able to write software to help us do this and make it easier? We also learned that engineers don't like mystery. In the early days with Control Tower, people were resistant because it was doing things that they didn't understand. It may have been doing things they were doing before, but it didn't tell them it was doing it. So one of the really important things we learned is that now Control Tower is very explicit about what it's doing. It lists what it's doing at each step of the way so that engineers can be confident that it's doing every step that they think it should be doing, and they don't have to worry about that. They can think about other more important things. Also, automate the process you have, not the process you want. When we started, we thought we could bring some process improvements in Control Tower through this automation. However, engineers were also resistant to that. They wanted to keep doing things the way they had done it. That's just kind of how engineers are. They like their process. And so what we found is we had to automate the way they wanted to do it, and then after that, we could build in some new features and give them the option to start doing things a new way. And that's an avenue to improving things over time without just shoving it at them. It gives them that option to go with it when it makes sense for them. So what's next? Where do we go from here? Well, we still think we have too much human interaction. Those 15 clicks in Control Tower, those shouldn't be necessary. It really shouldn't. We've started to hand the process over to machines. We think we can keep doing that. We believe that using modern algorithms and machine learning techniques, we can train code to understand which features are ready to release and which features are risky and need a person to look at them. Developers should be able to push code to production with very little human interaction. That's where we're headed. And if you're interested in hearing more about that, please follow our social media and our engineering blog. Thank you.